right? So here's the expression that I want you to copy down. As I said, the general form of the variance. Now, again, the textbook uses a bold B. I don't quite like that symbol because it's I prefer beta hat, right? So beta hat is B. This textbook uses B. The variance of the beta hat term is sigma square. See, I really find that the textbook uses the bold sigma for var. I don't like all these things. I prefer to write VAR beta hat. This sigma square is not bold. This is a scalar. This is that sigma square term that belongs to the variability of every term like that. So you have sigma square x prime x inverse. That's the expression for the variance of beta hat in general. 5.928 is a specific one. Take your sigma squares out, like what I've done. So do you find you have a, first of all, does everyone have a 2 by 2 matrix? Very good. It looks pretty bad. And if you want to save some algebra time, maybe it will save you a bit of writing if you just call the bottom this sigma xi minus x bar squared. I mean, that's an expression. I just don't want to introduce more lingo, but it will save you some time. Some people call this thing, the bottom part, SXX. They call that SXX, the denominator. You might want to do that because you're going to be writing it quite a bit. So you might want to save yourself the trouble, call it SXX. Right? I'll tell you why. It's called SXX because it's like the variability of x with itself. That's the history. So it's called SXX. So you don't like that, don't worry. You can just keep writing this thing. It's okay. Now, here's what I want to point out also. Can you see what we use as the estimate for this matrix? If you dump for sigma square, the MS resid. If you put MS resid as a number, you get what's called the estimated variance of beta hat. So I want to stress the variance of beta hat is an unknown quantity. The variance of beta hat is unknown because sigma square is not known. But you can estimate it. We estimate sigma square by using MS resid. And if you dump MS resid everywhere, you get the estimate. But anyway, that's not the point of this exercise. So you've written down today's exercise is an exact one. We're not going to do any estimation. We're just going to derive an expression. So var beta hat is that thing. Then can you answer a few questions? Looking at 5.92a, which you have written down, can you answer a few things? What is cove beta naught hat beta 1 hat? Now I'm asking this question for a specific reason. I want to know whether you actually understand what you're writing. What is the var beta hat giving you? It is actually giving you these things, these expressions. What is the covariance of beta naught hat, beta 1 hat? Anyone want to answer that question? Can you tell me what is cove beta naught hat, beta 1? What is the covariance between those two estimated? Does anyone know what? Yes. Actually, yes. Good. It is the off diagonal. Okay, good. So specifically, it is, let me try a mouthful. It is minus x bar sigma square over sigma xi minus x bar square. That's called beta naught hat, beta 1 hat. Very good. You know why? Because covariances are given by the off diagonals, as Anya has said. Very good. You do understand what a variance covariance matrix is. It tells you how those estimators, beta naught hat and beta 1 hat, how they behave together, how they covary. Excellent. That's really good. So write that down. The expression for cove beta naught hat, beta 1 hat is here. Now, I hope you're not confused by the 0 and the 1. Basically, the order is like this. If you line up your betas from beta 0, beta 1, beta 2, then the covariance terms also go in the correct positions like that. All right? 0 and 1. If you had a more complicated model, then your variance matrix will be bigger, and so you will have other things as well. Is this okay? Anyone want to answer the other one? What is var beta naught hat? Yes. It will be the 1-1 entry, correct? Is that okay? So if you want to save yourself some time, I will accept. You can say the 1-1 entry of 5.928. That's fine. But there's no harm writing it down a little bit clearer. And I hope you all are not confused. Because some students, they'll say, but didn't Professor Cole just say that the variance of y is always sigma squared I? Yeah, that's the variance of y. The variance of y in the linear model is, as Kelly said, sigma squared I. That's correct. But this is not y. This is beta hat. The beta hat vector has terms which have variances and covariances of them. Now, one thing I like about this class is I believe I'm offering you in this class more than what the undergraduate experience in learning statistics does. This has gone way beyond. A lot of people teach these things in very piecemeal ways, where they say, here's the expression for the variance for simple linear regression. Here's the expression for this in multiple linear, and it just gets more and more complicated, and you have tons of formulas. I'm just trying to tell you that everything actually comes from matrix algebra. And this is a specific example. So you can always derive these things on your own. See, that's the whole point. Okay, let's go on. What's var beta 1 hat? Anyone? In fact, isn't it interesting? Var beta not hat and var beta 1 hat are not the same. What's var beta 1 hat? The 2-2 entry of the. Very good. Okay, let's answer another one. For the specific choice, if I chose this vector 1xo, what will A prime beta represent? If you can get this, you will make me a very happy man, I'll tell you, right? What is, can you compute A prime beta first? Right, with this specific choice A prime, A prime is 1xo, like that. Can you compute A prime beta? Okay. First, I hope you realize A prime beta is going to be a scalar, right? Because you have a 1/2 multiplied by a 2/1. What do you get? Anyone done the computation? Can you read off what do you see? A prime beta is say it again. Beta naught. Very good. Simple enough. Scalar. Can anyone tell me what this is? Okay, stare at this model, stare at that expression for the simple linear regression model. What is beta naught plus beta 1 x O? Like that. Think carefully. What is this? First of all, this is a fixed quantity. I hope you realize it's not random. It is fixed. It is a function of the parameters, but what is it? If you had to tell someone, a lay person who doesn't know what statistics is, what is yes? Yes, you could. Yes, that is y0. But can you express it not as a random quantity? This is one possible value of y0, correct? But think of it long term. What is this long run? What is this? Yes. Anyone want to try? This has a long run interpretation, not a localized one just for a specific value of y. That's good. This could be a value of y. In fact, that opens another can of worms. But what is this long term? What is this? Yeah, it is. See, you will see that this is part of this model, but somehow the epsilon is gone, and somehow I've replaced this with a specific value of x. What am I getting at? Are you getting more a little bit? What is this chunk of the model? Yes, well, and line stays fixed, right? So this expression is actually the, okay, let me point you in this direction. How do I get rid of epsilon? What do I do to both sides of the equation to get rid of this epsilon term? No, if I subtract, it goes here, right? What operator do I put on every term to get rid of it? I'll give you that. What can I do to this expression that will make this go away, that will turn this to zero? See, the noise is not always zero, it's unobservable. But there is something I can put an operator in front that turns this term into a zero. What is that operator? What do I do to make this thing have no more epsilon term to contend? Does anyone know what it is? That's a very good try, and that is correct because we do estimate epsilon by treating it as a zero. That's correct. But not by doing that. What can I do? Think 365. What can you do from a probability clause that will help you get rid of somehow I can turn this into a zero. So model assumption. You know what to do.
Check the variance.
You're very close. It's not a variance. Not a, yes. In fact, no. The variance of epsilon is not zero. The variance of epsilon is sigma squared. Okay, you're very close. You're almost there. What can I do? Take the E everything. So if I E everything, I get EY, right? What is E beta naught? Is this a fixed quantity? Yes. So E beta naught is? Yeah. Is this a fixed quantity? Yes. And I told you specifically, if I asked you, find the expected value of Y. Now here's an expression which may be new to you. It's not a conditional mean, but it is used to express the fact that I am fixing my x at the value x. It just means if my x were at x naught, then we will agree that this is beta naught plus beta 1 at x. And the E epsilon has gone away because we know the model assumption in the linear model is that expected value of noise is zero. Good. So I hope this kind of learning process helps iron out some misconceptions. All very good tries. Very good. Excellent. So have I answered the question? What is A prime beta? A prime beta is. Can you express this in words? The not estimated, expected. That's right. Yes. So this thing that you have found is the expected value of y when x is x0. Now let me ask you, is this a useful thing? Yes. Don't people want to know what the mean value of y is for some particular experiment? That's the whole point of linear regression. You want, and now to answer what Anya said, like, is this a predicted value of y? Yes. The number beta naught, if I put hats on this, you are actually 2 in 1. Buy one, get one for free. You're basically doing this because this expression serves two purposes. Yes, it is a predicted value of a future observation. It is also what you would tell someone is your prediction of what the mean is. It does the whole. And I've said this before to my students, but not in this class. If I asked you to predict the mean height of Hope students, you would use probably the simplest idea is the mean height of Hope students. But if I ask you to predict the height of one future Hope student, wouldn't you give the same answer? See, that's exactly what's going on. Your prediction for a future observation and your prediction for a mean are the same number. So what is? The confidence interval, though, is for a mean. Confidence intervals only exist for fixed things, not for future observation. So that's called a prediction interval. We are not going to cover this in class. We are only talking about confidence intervals, which only belong to fixed. Okay, so enough about that. I think you can now finally do the very last question. So, for the specific choice of this, show this. I will give you some time. So, what do I want you to do? I want you to show me that when I choose this particular A, which you have specified, which I've specified, write down what happens to this for the specific SLR case. You have already written down what var beta hat is, right? For SLR. Now I'm saying develop this expression, do a little bit of matrix algebra, and I've already given you the final answer. Then I'll talk a little bit about what is the significance of what we're doing here. This is a very, very important class because this expression is going to be seen a lot of times as we proceed. All right. So var a prime beta hat is that thing when your expression for var beta hat is 5.92a, this one. So do a little bit of matrix multiplication. Take it slow. It's not that hard. I want to see if you know how to multiply matrices carefully. All right. You know the rule, right? You have a choice. You either, I honestly think you should take this out. Maybe you all can start it off together with me. How would you take out this constant vector? Remember, is this a matrix? Yes, this is a matrix. That's why you learn the more general things. Anyone want to tell me? How do you expand var a prime beta hat? Anyone? Yes. Yes. Comes out. Yes. Correct. That is all you need to do. And now go insert 5.92a, write down what a is, do a little bit of matrix, and I'll leave you in some peace. Okay, it's not hard. This one's just a little bit algebra. It's quite satisfying, trust me. All right, so do it. Then we'll talk a little bit about this various expression. It's also worth a little bit of a mention. All right. So if you are stuck and cannot develop it until it reaches that nice form, what you can do is expand the answer and show that it's equivalent to what you want. Because it depends on how much of a algebra nerd you are, right? Uh, I've done more expansions than I like to admit, and so these things come a little bit more naturally to me. If it doesn't come naturally to you, you can break up this expression that you're supposed to show, and then show it's equivalent to where you ended up. If the two are the same, then it's fine. Right? You can expand this final answer that I've written down and see where it matches up with your calculations. And that's fine. Oh, I found it. By the way, 6.25 in the textbook, there's a typo, which is clearly nonsensical because this would cancel. So it's a clear typo. Can you knock off the extra? There's an extra X here that doesn't belong. Just wipe it out. 6.25 is incorrect. There is a typo in the textbook. So this X does not belong. Right? Just uh, just erase that. Okay. Essentially, I'm giving you a preview of where we are actually going with this one for a specific example. I actually got this from the textbook. See, do you see equation 8.58? They are trying to ask you to prove that, basically. Like 1 over n and x4 minus x bar squared. Okay, that's what I'm guiding you. Okay. Never mind. If you finish it, right? That's great. Okay, don't worry. If you have not finished it, I believe you're almost there. It's just a bit of algebra. It's a little bit sickening, not very, a little bit. I did it myself last night. Took me a little bit of But it's okay. Just a little bit of careful algebra, you'll be there. So you can hand it in to me next time if you got it good. I want to talk a little bit about this expression, okay? Do you notice why we want you to factorize it this way? The expression is very telling. It means that when you ask for confidence intervals for means which are close to what, then your variance will be quite small. You are rewarded for asking questions about values of x which are, right? I want you to stare at 8.58 for a bit. Stare at this expression. See, you can see clearly that this is trying to form a confidence interval. Now, we've not gotten to the confidence interval part yet, but you can see that a confidence interval is always estimate, t quantile, and then there's an s thing, and then this expression, right? Clearly, this thing depends on your choice of x0. So, can you answer this question? For what choices of x0 will you be rewarded with a smaller width of confidence interval? If you choose your x0 to be closer to, not
Closer to x bar.
yes, good. Choices of specific values of x0 that are close to x bar, you are rewarded with a narrower width CI. Does that make intuitive sense? In other words, if you pick a value of the predictor variable that is very close to the mean value of the predictor variables, your estimation is more precise. Which makes sense? If you pick distant things far from the mean, those are rare things, then you are punished by a wider confidence interval. And that is why this expression is useful. In the unfactorized expression, you don't see this structure. And that is why all the algebra you learn in high school is useful. So sometimes I wish when students say, when am I going to use this? When am I going to use this? Well, now. That is why you learn in middle school or wherever how to. Actually, when did you learn to expand things like that? Can you tell me in America? How old were you when you learned how to open this file? Was it high school, year one? Or middle school? Last year of middle school? Eighth grade?
Yeah, I think 6 or 7 grade. Yeah.
That's actually very early, you know. I did not learn how to expand this until
Foil, yeah. We learned foil.
foil,
Front, outside, inside. Yeah.
front.
First, like first, outside, inside, last.
Oh. I don't have a fancy thing. I the way we learn in school is just practice again and then explain. But anyway, the point is all those things sometimes are not, the use for them is not visible until much later. And that's why math is not for those that are for instant gratification. You're not gonna get it, right? Sometimes yes, there's some instant gratification, but usually it's very deferred. Years later, even all those trick identities, remember all those how do you expand a tangent a plus b and all kinds of things. See, I can't even remember. Shame on me, I can't remember. Wait. Tangent of a plus b is tangent a plus tangent b over 1 minus tangent a tangent b. Yes, I still have it. Okay. So since high school. But anyway, the point is all these things have a use much later. It is more useful to write it in this form than the one that you probably had when you did all those messy calculus expressions with all the this plus this minus this. Why is this useful? It gives you an interpretation where if this is not far from this, you will make your entire numerator smaller and you're rewarded with a smaller confidence interval, which is always a good thing. Can you see other more instant rewards? If your n is big, does that make your confidence interval shrink? Yes, that's another consequence of having a large sample size. Always a good thing. When your sample size is big, don't you know more about a process? Yes, so you're rewarded by confidence interval that's narrower. All this intuition only comes by looking at the mathematical expression. That is why this class has a reason to exist. It's a mathematical statistics class, where you look at how the math informs the statistical implications. Okay, so I've said my piece. That should be group work 18 days. All right. So at this point, I do believe you are also ready now. Why it's called 18A, I wanted to prep you for 19. So group work 18A is an additional one, which I felt was a pre-19 a little bit, so that it will make your group work 19 a little bit easier. So let me pass this out now. This uses the groove data set, which is on Moodle. Let me show you where it is. This is a combination of R and also writing. Okay, so you will need to use R, and I want you to go from scratch. Don't use LM. Right? I want you to do these things from scratch. So go check your old code for doing these things from scratch, and I'll give you time. Right? Take your time, work through this, and you need any help, just let me know. All right. It's very similar. So group work 19 is very similar to 18A. But it's using this data. So let me bring it there. It's using uh, R code for chapter 1. Yeah, it's using this one, the mileage and that. But here, there's no matrices. This is just using LM to solve it. But you can get your data vectors from here, which you will, right, to construct your design matrix and things like that. So this is like a revision actually of what you should already know about how do you make the design matrix for a simple linear regression model. So I need help, just raise your hand, right? I'll help. Do all these things until let me see. Just do till 6. Just work till 6, then we'll continue with class, right? Do till 6 first, and then we'll continue with class because you cannot do the 7, 8, and 9 and 10 yet. They are related to what we have done today, yes, but not directly. So I want to make the connection before we. So just do 1 to 6 first. Okay? Are we doing okay? Any questions?
Hopefully using the vector for the
What is the vector? Oh, beta cat. Yeah, so you can use this one. Yeah, this is always true for any linear model. Right? So just use R, right? To write down the expression, then use R to get the.
but you don't mind why.
Yeah, so the Y here is mileage, right? Oh no, oh, that's that.
No,
Sorry.
it's that.
The X is mileage, the Y is depth. That's right. Right.
Check like they have.
Okay. So you are having. Okay, so you're doing it through LF to check.
No, I was checking it, but
Yeah, you can do it. It's okay. Oh, okay. Then it's a function of mileage. What are you getting for being a head when you do that? Oh, yeah. Okay, that is like zero. So it's something. So let's find that in this.
wait, did you say that? No. But then we were like, and it was not that.
No, okay, so can I see your X matrix? So you have C line, C left.
Oh,
Oh, you can graph C. So
oh,
you
I said why is mileage not that?
change that, and then you research for where to see. Oh no, it's there. Okay, I just want you to see everything with the color. Yeah. Okay, that's it.
Yes, that makes sense up there.
Yes. Yeah. Did you get it? See?
Yeah.
Okay. The Y is
That's what I did.
here. And what did you say? X is also there. Okay. Oh, okay.
Well, I
Oh, you also you really you just like that. Okay. Okay. Nice. Oh, it's nice to the okay. It's nice to the why did you what does that next matrix look like? How do you okay. Okay. So your code is usable, but you must remember how do you write down your X matrix for an SLR model? All right. We are using the mileage to predict depth. So mileage is there, but what does your X matrix look like in an SLR model? Anyone? Mileage is here. All your mileage variations here, but what goes here? Right. Good. Also get that. Oh,
No, that was it.
okay, very good. And everything checks out.
Yes.
That's it. Okay. And I think once you fix the X matrix, everything should. So don't forget, a linear, not just SLR, multiple linear regression as well, that must always be a column of ones, because that must account for the intercept. Okay, I want to now turn your attention to the second part of the assignment. And to do that, we need to learn some new stuff. Uh, look at equation 8.48 and 8.49, right? So let me zoom in. First of all, it can be shown that this monstrosity has an F distribution. I don't know why this book likes the F distribution so much. I prefer the T, but you know that if your degree of freedom has a 1 in the numerator, then T square is F. Therefore, the square root of this thing has a T, a corresponding T distribution. I also want you to think more generally. They like saying this the number of predictor variables in your regression model. Actually, I can replace the k here by the k minus 1. The k minus 1. In other words, n minus k minus 1 has a more general expression in linear model. Does anyone know what it is? Does anyone remember? We have dealt with this a little bit. Does anyone know that saying n minus k minus 1 is specific for regression? But does anyone know a more generic way to say the degrees of freedom is Tn minus, it's okay, more generic than just k for any linear model? Does anyone remember this one? Unfortunately, this textbook teaches things from a regression standpoint and doesn't get generic enough. So you need to make a small note. That is one thing that takes care of all this degree. Does anyone remember what it is? Yes, good. This is always true for any linear model. Rank X. Right? N minus rank X. Which is why if your model is SLR, your rank X is, I mean, a vector like this, numbers like this has rank 2. So it gets confusing because people say, oh, there's so many formulas to learn. Actually, no. Learn this. You can use this specifically because for a simple linear regression model, what is K? How many predictive variables does a simple linear regression model have? One. So if K is 1, don't you have n minus 1 minus 1? Is n minus 2? Is that the rank of this matrix 2? Yes. So I don't know about you. I prefer learning this. But you should certainly put this as a note in your notes. Anyway, to get back to the point, this thing is what's going to help us to construct tests, to get a test statistic T, and to construct a confidence interval. So I want you to stare at 848, 849 a little bit. Do you see the structure is actually nothing to be alarmed about? If you want to test the hypothesis, and what is the null hypothesis? If you want to test the null hypothesis that this thing is some number, then use this test statistic. The null hypothesis is always a statement about the parameters. I can test whatever I want. This is a very generic form of all the hypotheses that you've been doing in class. Haven't you done, let's test whether beta 1 is 0. Haven't you done this? How can you be a member of this class and not know this hypothesis? You've done this like 1,000 times. This is a specific version of this. If I chose this vector carefully, in fact, I'm going to ask you now, what should I choose A prime to be so that I can test this? If I choose in an SLR context, if I choose my A prime to be what, I will be able to test this hypothesis, that the slope is 0. Anyone know what I'm getting at? What must I choose my A prime vector to be to single out this thing? See, this is a vector. This has two things, but this has just the beta 1. So if I chose this to be, yes, not 6, 0, 0, 0. Feel like a jungle, this is like a vine. Okay. No, I really freak out because I don't know whether this is gonna. I've actually woken up with a spider walking on my face, and this brought me back to that place. Actually, I'm sanitizing it. I've actually had one other thing crawling on my face that wasn't even a spider. I don't know whether you can guess what it could be. Okay, no, it wasn't a mouse. It was a cockroach.
Oh, I was gonna say centipede. Oh,
Thank God, not centipede yet. Yeah.
yeah.
You see, cockroaches, they don't freak me out, but they're just dirty, you know. And then they have these things on their leg that brush against your face. Mm. Give me a moment.
I feel like you're just a mouse. I've had mice like when I was on vacation, I've had them run around like that.
Really?
Yeah.
Where were you vacationing?
I was in the mountains. I was in the mountains.
Remind me not to go there, right?
No, I've never gone there again.
Real, actual. Were they mice or rats? You didn't stick around to find out. That is so gross. Okay. Did they bite?
No, no, they just ran around. There were two of them. They were chasing each other. Right.
Oh, so they weren't actually concerned with you, right? They were playing around with you.
Yes. Anyway.
Anyway, so yes, choosing this would isolate beta 1, which means in this case, I'm testing hashtag equal hash, not hashtag, hash equals 0. So in a generic test of A prime beta equals anything you want, insert in 848. Calculate your p value, get your p value from your. Do you see that? What about constructing confidence interval? Do you see that the ingredients for making a t-test and the ingredients for forming the CI are exactly? So I will now have you complete questions 7 through 10 for this example. I know I use C in the assignment here. It's A, it doesn't matter. It's some constant factor. C is more common. I don't know why this textbook uses A, but I mean, that's a very small point, right? It doesn't matter. Right? So you use equation 848 and 849 to answer the remaining questions in the group work. And actually, after you are done with this, that is all for class. So you can stick around, finish it, and let me have it. Then you can go. That's all for today. I'm not going to go on. And please, okay, use R. I don't want you performing tons of matrix calculations. Use R to get these things. I think you know enough R now to tell R, okay, here's the A I want. Call it A if you want. And go perform these things in R. Right? Now, you do know how to do this by hand, right? If it's small enough, you do. But you can use R to save you some time. You don't have to do it by hand. I also want to point out the fact that this is very, very versatile. Every other stats textbook will teach you how to find confidence intervals for the individual data and things like that. Do you realize how much power I'm giving you? I'm actually teaching you how to construct any confidence interval for any linear combination of the data under the sun. Anything you like. Right? Remember those things in the first exam where I said, go construct a confidence interval for mu1 minus mu2 plus mu3 over 2. Remember that question? This kind of thing. Do you realize that this is a thing here? If I chose my A vector appropriately, you would actually be doing this. These two equations are the key to any linear model. It's amazing. The whole linear model theory can be encapsulated in 2 or 3 equations, and it feels true. But the lead up to this takes time, and that's why you have to learn all the infrastructure that goes behind one.
Is the S on that? Is that like a?
Right? That's a very good point. What do you use as the estimate for S? Anyone remember this? We talked today about this. S squared is estimated using the, you remember, I did talk about this. S squared is always estimated in any linear model by MS resid. Remember that.
I was just wondering if it's like.
The book calls it MSE. Yes, the book calls it MSE. I call it MS resid. I don't like these words.
I feel like the S root or like S times the square.
Right. So, oh, okay. That's a very good point. It's not the S root, it is S times. So, if S squared is MS resid, S is always estimated by square root MS resid. And this is true for every linear model. And do you know how to find MS resid, of course? MS resid is SS resid over what? Anyone remember the more generic version? It is always SS resid over N minus.
That's right there.
Yes. Oops. I hope everything is clicking now. I know that when you all learned this last time, oh, N minus 1. Yeah, because the models are different. They are all linear models, but they have different design matrices. The generic one is easiest to learn. N minus 1. That is it. So make sure you have these things written down. MS resid is always used to estimate S squared. MS resid itself is SS resid over N minus rank X. And you know how to find SS resid, right? That's just the sum of squares of actual minus predicted, right there, which are also used. All right. So try to finish this assignment. And when you're done, just let me have it. If not, you can bring it back next. All right. But that is actually all I'm going to cover today. So of course, I'll still be here. Any other questions, just ask.